Ankit Jain, Piero Molino, and my supervisor at McGill and Mila, Will Hamilton. So I'm going to go through these slides fairly at a normal pace, but do feel free to stop me at any point if you have questions, especially because I understand the background here is quite diverse, and me myself, I'm not a network theorist, so I'll probably learn a lot from your questions as well. So in this work, we're really interested in this idea called few-shot link prediction, where there's multiple ways to frame it, but in this talk, I'll frame it as such. So imagine you have a very single dense graph, but you only observe a very sparse graph. So it's illustrated in the figure where you see that many of these edges and the sparse graph that you're actually observing are missing. And additionally, we can make another assumption where you have this data generating process where you can subsample multiple sparse graphs for training. So you can either subsample this from this larger graph, or you can assume that there's some generative process that is generating all these graphs, but you can only observe a very sparse subset of them. And the goal really here is to do effective link prediction from a new graph that you observe from this data generation process. So one easy example is that imagine you have a biological network or some biological process, so there may be some protein-protein interaction that's happening, and that's generating many different types of graphs, but you're only observing a very small subset of the actual graph, and you want to predict something about some new interaction that happens. There's also many use cases in actual transportation networks, and in this particular case of this talk, we'll see that because this work was done at Uber, there's some actual use cases for Uber Eats, which you can frame as a graph where users are nodes and restaurants are another nodes, and if a user makes an order for a specific dish, then you have to reform an edge. Okay, so as I was mentioning, the motivating example for this talk is really this idea that in the use case for Uber was really, imagine you have multiple different cities and you're trying to launch this platform called Uber Eats. And if you're not familiar with Uber Eats, what it essentially is it's an app which lets you order from restaurants that are local to your city. So imagine you have the service already launched and rolled out in cities such as Montreal and Toronto, and then you want to launch this new service in a new Canadian city called Vancouver. So there are certain things that are very similar that you should be able to leverage when you want to launch this in a new city in Vancouver. And the first similarity really is that much of the graph characteristics will be similar. For instance, if I like, say, Chinese food in Montreal, Toronto, chances are I'll still like it in Vancouver. So although we may not have any new data in Vancouver, we can make certain informed predictions already. So these priors that were kind of learned in previous graphs, which are graphs of Montreal and Toronto, should somehow inform the predictions in this new city, Vancouver. So how do we actually leverage this graph structure when we have very little data? So this is the actual problem of few-shot link prediction, where we can only observe very few instances of these nodes and edges, but we still want to do useful link predictions. And the reason this is important is because this problem can be cast in a variety of different ways, not just in this trivial or contrived Uber Eats example, but this appears in many different settings, and I'm sure there's many examples you can possibly think of as well. Okay, so we'll dive straight into it. So for background and notation, we'll just assume that we have some distribution over graphs that are coming from a common domain. And I use this term very loosely, and I'll denote this as P of G. And P of G, what this essentially means is that we have some data distribution over graphs, and from this data distribution, we're drawing individual graphs. Each individual graph is now characterized by its node set, its edge set, and then additionally, each node can also have a d-dimensional feature vector that we can use. You can also represent this as an adjacency matrix. But the key distinguishing between our setting and many other previous settings is that we'll assume that the edge set is a very, very, very small subset of all edges in this one particular graph. So this could be 10%, 20%, or even 30% of observed edges. Now, typically when you do link prediction, which is the common problem, we usually have access to more than 50% of edges, which lets us really use a lot of interesting machine learning algorithms. But when we have very little data, in this case very sparse data, we'll find out that many of the previous machine learning approaches don't actually perform as well as we'd hope. So the real challenge here is how do we actually get performant algorithms when you have sparse data and you have a lot of sparse data in the form of multiple different graphs. So I hope the setting is kind of clear, and we'll see more examples in a second. So as I understand, the background here, maybe not everyone's familiar with graph neural networks, so I'll just give a very quick high-level overview of what GNNs are, and maybe this will help clarify a lot of the future notation. So really, as I mentioned in one of my earlier slides, the goal of learning using graph neural nets is really to learn these embeddings of the original network in some lower dimensional embedding space. So one key component of doing this is defining a similarity function, which is if you give me two nodes from this network, how similar are they? And really, this can be thought of as an encoding function. So the entire field of graph representation learning can be framed as learning an encoding function and a decoding function. The encoding function takes in a network and produces node embeddings and sometimes even graph embeddings, and then the decoding function takes these representations and does downstream predictions with them. So in our case, one simple prediction could be, what is the cosine similarity between two node embeddings? And that will tell you the likelihood of an edge existing. So when we want to use graph neural nets, the key idea is that we want to leverage information across a particular node's neighborhood. So imagine you have a target node A. We want to leverage the graph structure and sometimes even other information and update the representation of this target node. So this often boils down to quote-unquote message passing, where we send messages across the edges to this target node, and then we aggregate this information, and we use this aggregated information to actually update one's own internal representation of node A. So essentially what this boils down to is that we send a bunch of targeted messages from the neighborhood, the local neighborhood of node A, and then we use a neural network to actually modulate the information and learn some nonlinear representation for node A. So in equations, what this essentially means is that imagine you have an input node feature matrix, so call it XV in this case. And now what this does is that given XV and the adjacency matrix, we can now compute a weighted average of a particular node's local neighborhood and use some nonlinearity to update its own internal representation. And you can do this multiple times for a different layer. So HKV over here in this would represent the kth layer of node V's representation. Okay, so once we have a specific representation for each node in the network, we can then aggregate this after k layers and then apply any specific loss function we want to train the aggregation parameters. So one typical loss function, if you want to do generative modeling, would be to increase the log marginal likelihood of the data. Another loss function could be predicting the likelihood of missing edges, which is the one that we will use in this talk. So again, let's go back to the problem of few-shot link prediction. So the key distinguishing feature of this problem is that you have a distribution of a graph. So we have graphs G1 to Gn, which is now the empirical distribution. However, for each graph G1 to Gn, we can only observe a very small subset of true edges. So let's say 30%. And the goal is to learn this global link prediction module, which essentially does the following. If you give me a new graph G star from this distribution, I want to be able to do good link prediction with only few observed examples from G star. So that is the key challenge that we want to address. So maybe you're familiar with few-shot learning. So few-shot learning is a common problem nowadays in many supervised learning and even reinforcement learning setups, where really the goal is we want to train a model that can quickly adapt to a new task with less data. And this data set D defines a distribution over all tasks. So in the supervised learning setting, a task could correspond to distinguishing between two classes in a larger data set. So for example, if I wanted to distinguish between cats and dogs in ImageNet versus distinguishing between alligators and crocodiles in the same database, but these are two different tasks now. So there are many proposed approaches to solving this few-shot learning task. One approach that's been popularized over the past couple of years is this idea of gradient-based meta-learning. So the main message here really is that we want to learn some shared set of parameters theta that are effective as an initialization point for all tasks. So the main feature of gradient-based meta-learning, and one of the most famous algorithms in the setting is called model agnostic meta-learning, or MAML for short, is we want to essentially do two steps. We want to first update our set of parameters specific to a task, and we will also have a second order gradient update that will update across tasks. So what this boils down to is this loss function here at the bottom, and I won't go into too much detail here because this is not super important for this talk because this is specific to the supervised learning setting, but you can see that there's two gradient updates here that will happen. There's an internal gradient update, which is over a specific training set, and then if you differentiate this loss again with respect to parameters theta, there will be a second order gradient. So because MAML uses second order gradients, it can be sometimes very computationally expensive. So this is another key a characteristic of these algorithms is that because they use second order gradient information, they're using local curvature information, they can be often computationally expensive. So just in pictures, what MAML is trying to do is it's trying to learn this set of parameters theta, which acts as a good initialization point for, in this example, 3 different tasks. So we start from theta, and with maybe a quick gradient update, we can quickly converge to a very good set of parameters for task 1, task 2, or task 3. But most importantly, to converge to task 1, task 2, or task 3, we have to observe few examples from these tasks. And that's why this is called meta-learning, because we're trying to meta-learn this initialization point so that we can quickly adapt to this new task. Okay, so in this setting, how does few-shot learning actually relate to traditional meta-learning as I described it? Well, in generally, few-shot learning, we're concerned with the distribution over tasks, but in this work, we consider the distribution over graphs. And as we know that each graph is non-IID, which is not the usual assumption in typical meta-learning. So we're already breaking a few common assumptions. And we'll see how this actually impacts performance quite a bit. Okay, so what is the high-level approach? So the high-level approach that we're going to propose in this work is called metagraphs. And in general, we're trying to learn 2 sets of parameters. We're trying to learn, a local link prediction model, which will do really well on a specific graph. So we'll call this set of parameters phi I. And essentially, phi I will be tailored to a specific graph GI. But we'll also use a global set of parameters theta to initialize phi I. And this will be our quote-unquote meta-learner. And this global set of parameters theta is optimized over our entire empirical distribution of graphs. Additionally, we'll also learn what's known as a parametric encoding for GI, which will act as better initializations for both theta as well as phi I. So we'll call this parametric encoding a graph signature function. And the high-level idea is as follows. So imagine you've already observed many graphs, and you observe a new graph that you want to do effective prediction on. So the key question you want to ask is, like, how similar is this new graph that you're observing to all the previous graphs you've already observed? If it's very similar to one of the graphs you've already observed, maybe you don't want to change the set of parameters theta and the corresponding set of parameters phi I a lot, so you don't change this. But if it's very different, this new graph that you're now observing, you want to quote-unquote shake the parameters of theta so that it converges to a better local minimum. So in some sense, this psi of GI is now informing how much change we want to actually enforce on a local link prediction model. Okay, so one way of defining a local link prediction model is taking a variational graph autoencoder. So if you're familiar with VAEs in general, this is a very similar model, but it's been adapted to the graph setting. So essentially what we do is that we have an inference network that takes in your adjacency matrix as well as your node feature matrix and gives you an approximate posterior over latent node features, so Z. So this is our Q model. And then we have a generative component, which essentially, given 2 node embeddings, we will simply use a dot product decoder to predict the likelihood of an edge existing between 2 nodes. So you can imagine this model is inherently inductive. So if we can get node features for every node in the graph, we can then compute this dot product and predict missing edges for any possible combination of nodes U and V. And we obviously optimize this model using the evidence lower bound, or the ELBO. Okay, so as an overview of metagraph, I just want to reiterate the fact that we're trying to learn 2 sets of parameters. the first parameter is a global parameter theta, as well as we're trying to learn this graph signature function, which essentially takes in this graph and will now influence the local model parameters Q. So there's two link prediction models that are happening. One is with respect to parameters theta, and then one is with respect to the local parameters phi I. So both of these are optimized differently. The local link prediction model will be optimized using observed edges for a particular graph GI, while the global link prediction model will be optimized using second order gradients. So again, as I mentioned, why would we want a graph signature function? So specifically, you could interpret the graph signature function as like a graph embedding of sorts. It directly modulates the parameters of the local link prediction model, and we'll see how that happens in a second. But as I mentioned, the high-level idea is that very different test graphs should force the inference network to actually have very different optimal parameters. Okay, so what is the graph signature function? So you can use another GNN model. In this case, we can use a GCN model, which essentially takes the input graph and gives you node embeddings for each of the nodes. And then we can simply use another nonlinear ML function, such as a common MLP, to give a global embedding for the graph. However, one thing we want to do is that we want to use this graph signature function to actually influence the network parameters for the downstream local link prediction model. So to do this, what we essentially have to do is that we have to learn this graph embedding for every single layer of the local link prediction model. Essentially, if my local link prediction model has, say, 3 layers, I want the parameters of this local link prediction model to be modulated with the graph signature function. So my graph signature function will output 3 different embeddings, one for each specific layer. If you're familiar with hypernetworks, this is a type of hypernetwork where you have one previous network generating the parameters of another network. So as I mentioned, the graph signature function is simply another GCN or graph convolution neural network, and essentially the kth layer node embedding follows the following update. So we have messages that are coming, and it's denoted by M in this equation, from all nodes in the graph, and we're using that to update the internal representations for node V. And specifically, we can choose the function M for messages, and this can be different aggregation functions. I won't dive too much into details on different possible aggregation functions in the interest of time, but there's many different variants that we tried out, and they can be found in the paper. So just at a high level, one specific aggregation scheme is that we want to take a convex combination of, say, different node embeddings. So specifically, one way of modulating my local link prediction parameters is that imagine I use my graph signature function to give me 3 sets of parameters, so beta, gamma, and rho. And then for each of these parameters, I want to do a convex combination for specific node embeddings in my downstream local link prediction model. So maybe a picture is easier to explain. So in this example over here, or in this diagram, if you give me a new graph GI, I will learn 2 different things. I will first use the graph to actually compute my graph signature function, and then I will propagate this graph through my encoder model, but the weights of the encoder are determined by the graph signature function. Now, once I have my encoder weights, I can actually encode my graph, and I will get my inference parameters, so my posterior distribution over nodes, and then I can use that to compute the missing edges using that dot product decoder. So this encoder model is shared between a local link prediction model as well as a global link prediction model, but they have 2 different sets of parameters. So there's a local update as well as a global update. So if you're familiar with graphical models, there's 2 different graphical models that we can look at. The first model on the left is what people would do in the supervised learning setting, where you would have regular meta-learning or model-agnostic meta-learning. The diagram on the right is specifically the metagraph algorithm. So over here, we'll notice that there's 2 sets of parameters, again, theta as well as phi, but also this graph signature function psi, which is now informing the parameters of my local link prediction model. So there's this key difference we'll see that makes a huge impact in performance, because we're encoding prior information through this function psi. So experimentally, you can ask, how does this work? So we can break down the experiment into 4 different questions that we want to ask. So how do existing approaches perform in sparse regimes? And just common attempts at pre-training actually help. And then the next question you may ask is, does metagraph actually lead to better performance? And then finally, we really want to answer, what is actually being learned by this graph signature function? So to test this approach, we tried 3 different data sets. We tried a protein-protein interaction network. We also tried a robotics network, a robotics point cloud data set rather, in first MMDB. And then finally, we tried a citation network in ego A minor, where we computed ego graphs for a really big citation network, and we subsampled 72 different graphs from this. So each of these different data sets have very different characteristics in terms of their structural patterns, as well as number of nodes, edges, and also the node features that are used. So answering question one.
Yeah, sorry, can you just quickly clarify what is the PPI network? I think the signal blocked at that time. Yeah, sorry.
Sorry, I didn't quite understand the question. Could you repeat that?
Oh yeah, can you repeat what was the first experience? The PPI dataset?
Yes, PPI is a protein-protein interaction network. So it's a biological network where you have interaction between 2 different sets of proteins, and you want to see how well binding happens, if you will. I'm not an expert in biology, so I can't give you more details than that, but this is a very common data set that people use as a test bed. Hopefully that clarifies it a bit more. And I guess I should mention that the node features are part of the data set. So for ego A minor, we used the average word embedding or glove embedding for the abstract. Okay, so answering the first question, how do previous existing methods do? So on the x-axis, what we have here is the percentage of training edges observed across all graphs. So we consider multiple different baselines. We consider classical Adamic-Adar methods, which is purely based on neighborhood statistics. We also try random walk approaches, which is deep walk, which essentially does a random walk to estimate the node embedding. And then we also have a typical variational graph autoencoder without any meta learning at all. So already we can see that when we have very little edges across all the data set, the models are not very performant. But as you increase the number of observed edges to say 70%, interestingly, a lot of the classical approaches start doing really well. And this kind of makes sense because these approaches, like Adamic-Adar, are not inductive. So they're very specific to how much data you have available to you. And finally, we also considered another baseline where we don't consider any graph information. So we considered an MLP, and we just use the input features of the node feature matrix. And we see that this model doesn't really perform that well either. So the next question we want to ask is, does pre-training actually help? So again, we have the same construction as before, where we observe 10 to 70% of edges. But now we also want to try this approach of where we pre-train the model. In this case, it'll be a VGE again, where the model parameters are updated sequentially. So if you give me graph 1, I converge my model parameters to graph 1, and then I observe graph 2. Then I use my previous set of parameters to do well on graph 2, and so on and so forth until I reach graph n. What we find is that in this setting, this pre-training approach is not as helpful. So if you look at the 10% regime, the very first column for PPI and even first MM, we notice that the amount of performance boost is very minimal. And then the next question is this, okay, what if we do this variational graph autoencoder approach, but also use second order information and MAML? Does that actually help? So it turns out that can help sometimes. So if you look at specifically the columns for 10 to 30%, we notice that there is some performance benefit. But again, if you look at the very last data set, which is A minor, we notice that this is not always helpful. So sometimes using just vanilla second order gradient information naively does not actually lead to important performance benefits. Then we can turn to our question of how much does metagraph actually help? So specifically, the main difference between metagraph is this idea of using this graph signature function. And through this graph signature function, we're actually encoding prior information between graphs. So we find that this actually helps quite a bit. So there's noticeable performance improvements in all data sets, but specifically if you focus on the A minor data set, we notice that there's a huge performance difference, especially in the 10 and 20 and 30% regimes, almost 10 AUC points.
Could I ask a quick question?
Mm-hmm.
How are the graphs subsampled? So when you're talking about these sort of ablated graphs, is it 10% as in you remove 90% of edges or nodes? And if so, was that IID or
Right.
something else?
So graphs are, so when we remove edges, we can only observe, say, 10% of the JCC
Right.
matrix.
So you're not
So
removing
all
nodes,
nodes
you're
are,
just removing edges.
no, we're
Okay.
only removing edges. That's entirely correct. I should have clarified that a bit earlier. So yeah, when I mean X% of edges, the graph is equivalent to saying I have a sparse graph from a larger dense graph. So we only observe a small part of the JCC matrix. Okay.
Thank you.
Yeah, hopefully that clarifies that question. So again, in terms of raw numbers, we observe about a 5% improvement over MAML and a 5.3% improvement over previous pre-training improvements. And more importantly, we find that this metagraph approach actually maintains strong performance with only 10% of data, which is the exact setting that we were interested in. So you might be interested in knowing how well does this algorithm perform with respect to gradient updates. So because this is a few-shot algorithm, we expect it to do well with only a few gradient updates. And as you can see over here, so the very final line, the I guess orange brownish line over here is the graph signature function, and we notice that it converges almost immediately to the final set of optimal parameters very quickly. And we can reconcile this observation by just rethinking about the fact that the graph signature function is aggregating information of global graph properties and using that as a prior to actually enforce or inform the local link prediction model. And we see this trend across multiple data sets. So again, it's the same story. And interestingly here, in this particular data set, we find that if we don't fine-tune, which is just have a separate VJE-AE model for individual graphs and just average the information, it doesn't do well at all. So the next question you can, as I alluded to, is that what is the graph signature function actually calculating? So we tried a bunch of different heuristics, and we found that the graph signature function is actually very attuned to node features. So if you we calculated the average node feature or node embedding information with respect to the actual embedding of the graph signature function. So we took the node features and tried to find the Pearson correlation between them. And we found that in this case, the graph signature function actually correlates highly with the input node features. And this kind of makes sense as well. Because we're observing a very sparse graph, a lot of the structural information is already broken. So for effective learning, we really have to leverage node features, which is the input node features quite a bit. We also tried to find if there was any correlation between the number of nodes and number of edges and various other graph heuristics. And we found that the input node features to be the most important distinguishing feature for effective link prediction in a sparse regime. So in conclusion, so we've studied this new problem of few-shot link prediction. We introduced this metagraph approach, which is capable of learning graph-specific information to bootstrap learning for local link prediction models. Well, there's a variety of ways you could possibly extend this. One interesting extension could be that the graph signature function only modulates parameters using the current graph information. But if you had some sort of learned metric, which you could use to pairwise compare all different graphs in this data set, you can kind of tune your model to only pick up specific characteristics of a particular graph in your training set, rather than average global characteristics. So yeah, with that, I think my talk is done, so I'm free to answer any questions.